everyone, welcome back to Measure Theoretic Probability. When we last left off, we were talking about expectation or expected value for simple random variables. And today we're going to kick it up a notch and talk about expectation or expected value for more general random variables. Now, I don't know your exact background, but I have a feeling the definition I'm going to use for expectation today is not going to be one that you recognize. But if you stick with this course, you're eventually going to see one you recognize and the equivalents. So we're going to see at least 3 different ways to define expectation. Today, we're going to look at a general random variable and we're going to approximate it with simple random variables. We know how to take the expectation for those simple ones, and we're going to take the expectation through a limit. Eventually, not too far away, we're going to introduce integration. Now, this is still probably not what you're used to seeing because you're probably used to integrating against a PDF or probability density function. We are pretty far away from that, but we're going to look at expectation defined as integrals, and we're going to be able to deal with expectation defined as integrals even for discrete random variables. So the unification of the treatment of continuous and discrete random variables is always given as one of the first reasons, like on day 1 of a measure theory probability course for taking measure theory. It's really cool that we can do that. We are not going to integrate with respect to Lebesgue measure anymore. That is, we're not going to have dx on the end of our integrals. We're going to have a dp, where p is a probability measure, or a d mu, where mu is a general measure. And we'll probably start into that next time and spend quite a bit of time doing that for general measures. So you can use that outside of this course, even if you're not talking about expectation or even probability. Eventually, we will talk about probability density functions and define expectations that way. And as we go with these new definitions of expectations, we'll always keep track of how they're equivalent. So today might not look like something you've seen, but stick with me and we'll eventually see what you've seen and why it's equivalent. Let's get going. We have already defined expectation for a simple random variable. Recall, a simple random variable is a step function thing looking like this. Underlying this definition and everything we do here is a probability space. We've got a non-empty set omega, we've got a sigma field curly f, and a probability measure p. And for a function x on omega, taking values in omega and spitting out reals, to be a random variable, it needs to be measurable. That means the inverse image of Borel sets in R need to be in curly f. For a simple random variable, it's much easier to check. We just need these sets, capital A1 through capital AN, to be in curly f. I've talked about my definition, which really isn't out there in the world, of a canonical representation for a simple random variable. I usually assume that little x1 through little xn are distinct, and the sets capital A1 through capital AN are disjoint and forming a partition of omega. It's not necessary, but it is helpful in some proofs of things coming up. So once you have a simple random variable, recall that we've defined the expectation, whether or not you have a canonical representation, as basically a sum that looks the same, except that we've replaced the indicators with the probability measure of the sets being indicated. So this is old news. Today we want to look at more general random variables. We are going to restrict our attention today to non-negative random variables. If you've had a lot of analysis, I think you know what's coming next. It's not a big leap to move from non-negative random variables or functions to functions that have a negative part, because the negative parts are the negative of positive parts, and we'll do that in just a couple of lines in the next video. But for today, non-negative random variables. So suppose x is a non-negative random variable, measurability, all that is assumed. I'm going to denote the expected value of x the same way with a capital E of x, and it's defined to be the supremum of a bunch of expectations of random variables y, which are simple and trapped between 0 and x inclusive. So there may be a lot of things in here unless x is identically 0, and this sounds hard to compute. But we're going to narrow this down a little. Let's first consider, let's first ignore expectation. I have a claim for you. So if I have a non-negative random variable x, I claim that there exists a sequence, capital X1, capital X2 on up, of non-negative simple random variables that are converging to x from below, that are increasing to x. So you know what this upper right arrow means for real numbers, presumably. We are increasing, right? We've got a sequence approaching a limit, and the sequence values are getting, they're not getting smaller, they're staying the same or getting larger. And That's what I mean here when you look at this pointwise. So xn of omega is less than or equal to xn plus 1 of omega, etc. And those real numbers are converging up, increasing to x of little omega. Let's prove it, and then we'll go back to expectation and see why this is a helpful claim. To prove it, I'm going to give you an example of a sequence. And this example will work no matter what non-negative random variable you've chosen. So we're done. We've proven there exists one. Now, this is going to be a little confusing here. I'm going to give you an example of a random variable, but the example of the sequence we're going to construct does not depend on what I've drawn at all. This is just to help us. This is like a marginal note in the proof to say, what are we doing here? What does it look like when I have a real function or random variable that I'm working with? So again, the given example to finish the proof is not dependent on this example of a random variable. I'm just going to use this as an example to show you how we would build up simple random variables to converge to this. And again, that sequence will work no matter what you've drawn here. And I should say that usually, or not usually, but a lot of the times you won't be able to draw this because I'm making omega here look like it's a real axis, but omega does not even have to be numerical. We started out with omegas looking like sets of points like heads, tails, heads, things like that. So this is just a visualization tool, but the proof does not depend on what I'm visualizing here, if that makes sense. Let's see if it makes sense. Let's continue. What I'm going to do is I want to approximate this from below. Now, a random variable is real valued, so this axis up here is real numbers. So I do have a sense of below and above. I want to approximate this function below by basically a step function. I'm going to start by dividing up the y-axis into a bunch of pieces like this. I will be more specific in a moment. We're just kind of talking through the picture right now. And I'm going to use these lines to help create steps for me for a step function that's going to be a simple random variable. So I'd like you to first consider, for example, the little horizontal space between these two lines. I want you to look at where x of omega is in these lines. I've got some over here and some over here, and let's back up and see what omegas mapped us in there under x. So it appears that I have an interval here and an interval here. So all the omegas in here and all the omegas in here under x will map us into this horizontal slice. I'm going to define a simple function for all omega, but I'm going to start by defining it for these omegas. I want it to, again, look like a step function and be below our function. So I'm going to take the bottom pieces of the slice, like this, to define my steps for a simple random variable. Let's look at another horizontal slice. Maybe between here and here, I'm going to back up and say, what omegas map me into there? For these omegas, whether or not they look like an interval, or, this could be a lot of disjoint, weird stuff. And again, the horizontal axis is not even real numbers. But I'm going to look at any omegas for which x of omega falls into this horizontal slice. And for those omegas, I'm going to define my simple function to be the bottom of the slice. So a little hard to see down here, but this horizontal slice. So I'm going to continue doing this. And notice I am never saying for little omega between this number and that number, because omega is not necessarily numerical, but x of omega is. It's always real. So I'm talking about whenever x of omega is between two numbers on the y-axis, back up and figure out what omegas in what crazy space mapped us there. For those omegas, I'm defining x and omega to be a slice below where x of omega is. So I'm going to continue the slices, but before doing that, I just want to say one thing. If my x of omega was unbounded, then I am going to have an infinite number of steps to try to capture it. And that's not allowed for a simple random variable. So I need to put sort of an artificial top on these slices to make sure that we only have a finite number of horizontal strips. Again, if x of omega was a bounded function, then you can just start with a finite number of horizontal strips and you don't have to worry about this, but generally we might. Let's say I want to make this horizontal line up here like the top of the slices for my step function. I am going to say for any omega that has this x of omega above it, I'm going to define this horizontal line to be a piece of my step function simple random variable I'm trying to define. So out of these green horizontal lines I'm making, I'm basically never going to have a horizontal line above this one. I'm putting an artificial top on what's going on here. If we fill in the rest of the slices as we've been doing, we get a simple random variable that looks like these green strips here. Let me take the background out. This is a simple random variable that's sort of approximating the x of omega that I've drawn. But is it? Is it a simple random variable? It's a simple function. It's made up of a finite number of slices and a step function, but we do need it to be a valid random variable. So we need those sets defining the slices, the omega sets down here, to be in curly f. We need to make sure it's a valid random variable. Let's take a look in my example of these omega sets down here. Let's look at each level of slices. So this first level down here at 0 is defined by omegas looking like this. And I might call this set capital A1. And it only looks like this for this particular random variable. It could look really wild. The omegas down on my horizontal axis that define the second height step is in here. So maybe I'll call this capital A2. Let me do one more because the next one is a little more interesting. The third height slice, the omegas that give us that in this picture is a set that consists of two disjoint sets. Again, I don't know what your omega looks like or if it's even numerical, so this is just to visualize what we're doing. But as we go along, we have a capital A1, capital A2, capital A3, etc. Actually, we have only a finite number of them, and we need to make sure they are in F so that we get measurability of the functions and therefore measurability of the step function. I think we've got this. Number one, each capital AI is the inverse image under X, which is a valid random variable and therefore measurable, of an interval on the y-axis. Intervals on the y-axis are Borel sets in R. And X is a random variable. It is a measurable function, so inverse images of Borel sets are always in curly F. That's how X is a valid random variable. X is measurable, and therefore these AI as inverse images under a measurable function, they are in curly F. And these AI are defining our simple function, so our simple function that we've defined in this construction, definitely measurable, and therefore a simple random variable. So I think I kind of messed up the proof by, it's not wrong, but by introducing my marginal note on the main screen, we were looking at some example of a random variable. Let's just go back to looking at it very generically. Let me remind you of the claim. For every non-negative random variable X, there exists a sequence, capital X1, capital X2, on up of non-negative simple random variables that are increasing to X. To prove it, we just need to exhibit a sequence. And I am no longer going to use my example random variable to try to draw that sequence. Let's do it totally in general. And here it is. I'm just going to define it. I'm going to define xn of omega for n equals 1, 2, 3 on up to be a bunch of things. So let's look at this top slice first. I'm going to say n, I have a sequence when n is 1, 2, 3 on up. If x of omega is greater than or equal to n, that's where I'm going to cut it off, and I'm going to define my simple random variable to be at height n. And I'm going to make my slices have width 1 over 2 to the n, so we can make them shrink. There's other things we can do to make them shrink, but this is going to be a convenient way to define the slices. And so if x of omega is between 0 and 1 over 2 to the n on the y-axis, I'm going to define my step to be at 0. If it's between 1 over 2 to the n and 2 over 2 to the n on the y-axis, I'm going to define my simple function to be at that lower height, 1 over 2 to the n, etc. We can write that down like this. Basically, this is a piecewise defined function with n times 2 to the n plus 1 lines, but I wrote the first line over and over and over again like this. So if this looks weird to you, write it all out. You'll see a 0, and then a 1 over 2 to the n, a 2 over 2 to the n, a 3 over 2 to the n in the intervals, 0 to 1 over 2 to the n, 1 over 2 to the n to 2 over 2 to the n, etc. And again, there'll be n times 2 to the n plus 1 lines in your piecewise defined function. And we are done. I guess maybe we need to prove that it's converging. I'm going to leave that to you. It's not hard at all. So we need to prove a couple of things. One is that it is a simple random variable. We already talked through that proof. There's a finite number of steps, and each of the sets that we're using to define the steps in these random variables are inverse images of Borel sets. So it is a measurable function, a measurable simple function. And to show that it is converging to x, we know it's coming from the bottom because we designed these xn's to always be below x. But to show it's converging, you just want to show that for any given omega, so take an epsilon, you want to show that xn of omega is within epsilon of x of omega. So just make sure your slices, your 1 over 2 to the n, is small enough, because for every omega, right now, your xn of omega is within 1 over 2 to the n of x of omega. So take n large enough so that 1 over 2 to the n is below epsilon, and you're good. And we're done. So what does this have to do with expectation? Let's get back to expectation. If x is a non-negative random variable, and if xn in brackets is a sequence of non-negative random variables that are increasing to x, much like the sequence we just constructed, then I claim that the expected value of the xn's, which are real numbers, are increasing to the expected value of x, no matter what increasing sequence of simple random variables you chose. We have a construction. You may have a different construction, but it shouldn't matter what we use. Starting with any non-negative, measurable, simple random variables converging up from the bottom to x, we're going to get the expected values converging to x. So again, build your own construction, take the expectations. It's pretty easy to do. I'll show you an example at the end. Well, it's tedious, but not hard, but definitely tedious. And you're done. You have defined the value for the expected value of x. So let's prove this theorem. Again, xn increasing to x is a pointwise statement. This says that xn of omega is increasing as a limit of real numbers to x of omega, and specifically that xn omega is less than or equal to xn plus 1 omega, etc., for all omegas in capital Omega. It also means that xn of omega is coming up from the bottom, so it's less than or equal to x of omega, where x is that limiting random variable for every omega and for every n. We could replace these statements with a almost all omega and would be okay. And I think I'm just going to stick with this. It's a little cleaner, but it's not going to be a big deal to go through the proof again and deal with probability 1 statements. So let's prove it. First, I'm going to assume that x, the random variable here, is not identically 0. If so, we're done, because we need to look at simple random variables that are squished between 0 and 0, and that's just going to be 0. So all of the random variables in the supremum definition for expectation are 0. All the expectations are 0, and the supremum of a bunch of zeros is 0, and we're done. So let's assume that x is not identically 0. Because I want something to actually do here. And let's suppose all of the given stuff. So I'm lazy to write this out, but suppose that x is a non-negative random variable and xn is a sequence of non-negative simple random variables increasing to x. Let's suppose that. How are we going to show that this expectation converges? First off, I'd like you to note that because xn is less than or equal to xn plus 1, etc., we have that the expected value of xn is less than or equal to the expected value of xn plus 1. And this was, I believe, number 7 in a list from the previous lesson, or maybe 2 lessons ago at most. We showed that expectation maintains inequalities like this, and we talked about what an inequality for random variables even means. So expected value of x1, expected value of x2, on up, this is just a sequence of real numbers, and it's increasing. That means it's increasing to a limit. You may recall the bounded convergence theorem from regular analysis, which says that if you have a sequence of increasing or non-decreasing real numbers that are bounded, they are going to increase to a unique and finite limit. But if you don't have boundedness, they're still going to increase to a limit. It's just that that limit might be infinity. And that's okay. What we don't have is any sort of oscillation where it's not approaching anything. If it's going up, 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 if there's some kind of bound, it's eventually going to be squished below it and level off to something. And if there's no bound, it's going to keep going up and approach infinity. So This is a result from regular analysis. I have an increasing, or I should say non-decreasing sequence of real numbers. It's going to be approaching some limit, although it may be infinite. Let's let C be that limit. And again, C may be infinite. What do we want to show? We want to show that the expected value of x is equal to C, and then we're done, because we're trying to show that this limit is equal to the expected value of x. So if we show the expected value of x is equal to C, we're done. Recall that the expected value of x is a supremum of expected values over all simple random variables y that are trapped between 0 and x. Now, the random variables included in the ones you have to look at for this supremum is, this includes all the random variables in our sequence, capital X1, capital X2 on up. This implies that the ultimate supremum is greater than or equal to C, which is the limit for these random variables. Why is this? Let's suppose it's not true. So here I'm going to throw down a real line. I'm going to put a C up here. We've got a sequence of real numbers, expected value of x1, expected value of x2, etc., that are approaching C. Let's suppose that the expected value of x is down here, is below C. Now there's a space now, and if we assume that the limit of this sequence here is approaching C, we can get arbitrarily close to C. This means that these real expectation numbers that I'm plotting here are going to eventually jump the expected value of x. And this contradicts that the expected value of x is the supremum, or at least upper bound, specifically an upper bound, for these expectations over here. So we get a contradiction if we put the expected value of x down below C. Therefore, it must be greater than or equal to C. So we're partway there. We want to show it's equal to C. So now what do we need to show? We need to show it is less than or equal to C to finish this proof. I claim that we will have this inequality. The expected value of x is less than or equal to C if we can show that for every random variable y that is simple and trapped between 0 and x, the expected value of y is less than or equal to C. Why is it enough to just show this statement? Suppose that y is a simple random variable trapped between 0 and x, and suppose that the expected value of y is less than or equal to C, but suppose that the expected value of x is greater than C. Let's draw this picture. Here's a real line. Here's C. I'm going to assume that my y expectations, all the different values I'm souping over to compute the expected value of x, are down below C. So like down here. But suppose that the expected value of x is up above C. Then this means that there are smaller upper bounds for the y expectations. This means that even though the expected value of x is an upper bound for the y expectations, if the expected value of x is above C, then there's some space in there to get another upper bound on the expected values for the y's that's actually smaller than x. That's what happens if you assume the expected value of x is up above C. Therefore, it must be less than or equal to C. This is what we have to show. This is what remains in the proof for us to show that the expected value of x is less than or equal to C. And what we just showed in this picture is that we get that by supposing that for all simple y's trapped between 0 and x, the expected value of y is less than or equal to C. This will force the expected value of x to be less than or equal to C, and we're done. So once again, it remains to show that if y is simple and trapped between 0 and x, if the expected value of y is less than or equal to C, we are finished with this proof. So let's take a simple random variable y that is trapped between 0 and x. I'm going to say that it has, well, it's simple. So it has this kind of form. I'm going to say it's got m terms with coefficients little yi and sets capital B1 through capital Bm. And let's just assume that it is in my canonical form. So that means that all of these little y's are distinct. Otherwise, we can combine some sets, like if little y1 is equal to little y3, then let's just call them both little y1 and take away b3 and have our b1 be our b1 union, union with b3. You know what I mean. So if I assume this canonical form, though, then that means that capital Bi is specifically the inverse image under the y random variable of little yi. I'm going to take a small epsilon. You can do this with other upper bounds, but I'm going to say it's greater than 0 as usual, but less than or equal to 1. and I am going to define a new random variable that depends on n and epsilon. I'm going to call this y sub n comma epsilon. I'm going to define it to be 1 minus epsilon times y. So because epsilon is between 0 and 1, this could be as small as 0, but it's probably something a little bit less than y, if not all the way 0. And then I'm going to multiply by an indicator that forces us to look at the omegas for which x sub n is greater than or equal to this 1 minus epsilon times y. So note, among a whole bunch of things that we get out of this construction, is that y sub n comma epsilon is less than or equal to x sub n. This is not so hard to see. If you don't see it, I would rewrite y sub n comma epsilon in a piecewise form. I would say it's going to be 0 whenever xn is less than 1 minus epsilon times y. Now, xn is a non-negative random variable, and 0 is always less than or equal to xn. Then for the second piece, you say that yn comma epsilon is going to be 1 minus epsilon times y for the omegas for which xn is greater than or equal to 1 minus epsilon y. But for those omegas, our y and epsilon, which is 1 minus epsilon y, is specifically less than or equal to x sub n. So again, I think writing this out piecewise, if you don't see this inequality, is really helpful. Okay, so recall we've defined our y as a sum of m terms that look like this. Also recall that if you multiply indicators on sets, you get a new indicator which can use the single set, which is the intersection of the two sets, because the only way this indicator is 1 is if both of these are 1 at the same time. So omega needs to be in both sets A and B. And let's put this together. I am going to plug this expression in for y here. And then I am going to pull this indicator, which is like outside the sum, inside the sum. I'll get a product of indicators, and I'm going to use this fact up here to write this as a new indicator involving an intersection. So I have a pretty wild set down here. It's going to be a lot to write, so I'm going to give it a new name. It involves n and I and epsilon. So let's call it this entire set b sub n comma I comma epsilon, or whatever. Now we have y and epsilon written a little more cleanly. So this is just the line from the previous slide at the end with our new set notation. And we can take the expected value of this and run the expectation through the finite sum. As you know, the expected value of an indicator is the probability of the event being indicated, so this turns into a probability. Now I claim that the b and I epsilon are increasing in n to b sub I. Yes, doesn't even depend on epsilon. And I'm going to prove this after I finish proving this theorem because I think it's a kind of significant detour. So let's assume that this claim is true. Let's use continuity of probabilities to take a limit here and say that the probability measure of b sub n comma I comma epsilon increases as a sequence of real numbers to the probability measure of b sub I. If this claim is true, then continuity of probabilities gives us this result. So the expected value of y sub n comma epsilon looks like this. As n gets large, I claim that this increases to 1 minus epsilon, the sum as I goes from 1 to m of little y sub I times the probability measure of b sub I. But this sum right here, this is the expected value of y. Remember how y was defined as a simple random variable? This is the expected value of y. So we have the expected value of this y construction, y sub n comma epsilon, converging to 1 minus epsilon times the expected value of y. I want to combine this with the fact that the yn comma epsilon is less than or equal to x. I've got then that the expected value of y sub n comma epsilon is less than or equal to the expected value of n. Now this side is converging to 1 minus epsilon expected value of y. That's what we just showed up here. But this side is converging to c because we define c to be the limit of terms like this. So putting this all together, we have just shown that 1 minus epsilon times the expected value of y is less than or equal to c. We were trying to show that the expected value of y is less than or equal to c, but the epsilon in there being arbitrary between 0 and 1, we can shrink it down to 0, and that will force the expected value of y itself to be less than or equal to c. If you don't believe this, then draw a picture just like we've done at least twice today. Imagine that 1 minus epsilon, expected value of y is less than or equal to c, and shrink epsilon. And if you assume that this is actually expected value of y is greater than c, prove it with the same kind of argument we made today, you will end up with a contradiction. And we are done. This is what we wanted to show. And yeah, that's it. Okay, we're almost done. In that proof, I did use continuity probabilities to show that a certain sequence of sets was increasing to another set. Let's prove it. Specifically, I called the set B sub n, comma I, comma epsilon, and said that it was increasing to a set B sub I. Now, recall what it means for sets to be increasing. We need this inclusion. The sets need to be containing the previous set. And then when you union them all up, you need to be getting the set on the right side of this arrow. Let's start off with the fact that our xn are increasing to x. This includes the fact that xn is less than or equal to xn plus 1 for all n. And so consider the set of omegas. So I'm suppressing notation as I have been all day today. Consider the set of omegas for which xn of omega is greater than or equal to 1 minus epsilon times y of omega. This is going to be contained in the same set using xn plus 1 in place of xn, because xn plus 1 is larger or equal to xn. So it's going to be easier for this inequality to happen than this one. Therefore, this is going to potentially have more satisfying omegas in it. Similarly, this set is going to be contained in the set of omegas for which x of omega is greater than or equal to 1 minus epsilon times y. And that's for the same reason. I mean, if I continue this statement up here, this xn increasing to x also includes that xn of omega is less than or equal to x of omega for all omega and for all n. So that's how I get this inequality. Now, this set out here, I claim, is all omegas in capital Omega. And that's because the y that we are using, the y's in this proof, are always trapped between 0 and x. So every capital Y used today was always less than or equal to x. And 1 minus epsilon times y for epsilon between 0 and 1 is less than or equal to y. So 1 minus epsilon y is always less than or equal to x, no matter what omegas you plug in. And therefore, this set out here is the entire capital Omega. Now I'm going to take these inequalities here, or these inclusions of sets, and I'm going to intersect all of them with B sub I. Over here, when you intersect this with B sub I, this is the definition of our B sub n, comma I, comma epsilon. And when you do it here, this is our definition of B sub n plus 1, comma I, comma epsilon. And we said this is omega, so when you intersect this with BI, you just get BI, and this holds for all n. What are you seeing? You're seeing an increasing sequence of sets for the B's in n, which is one part of what we need to get this result up here. And because these subset statements hold for all n, if you union up this for all n, this will still be contained in BI. So what we have shown is that the union over n of B sub n, comma I, comma epsilon, we've shown that this is contained in BI. To finish the proof of this claim, we want to show the containment goes the other way. So I did this with sets, but to go the other way, I'm going to do it element-wise. I'm going to take a little omega in B sub I, and I'm going to show it's in this union. Let's do it. So I'm going to take any omega in B sub I. We want to show it's in this union, which means we want to show it's in one of these sets, B sub n, comma I, comma epsilon. What we're going to actually see is that it's in all of these sets when n is large enough. So recall that B sub n, comma I, comma epsilon is the set of all omegas for which x sub n is greater than or equal to 1 minus epsilon times y, and that set of omegas is intersected with B sub I. Now we're starting with a little omega in B sub I, so it's certainly already in this part, which means that it remains for us to show that for any little omega in B sub I, it's in this set here for at least one n. That means for that omega in B sub I, we want to show that we have the inequality x sub n of omega is greater than or equal to 1 minus epsilon times y of omega for at least some n. Now it turns out that it's not going to matter that this omega came from b sub I. It turns out that we're going to be able to get any omega in a set like this for n large enough. So let's show that. When I take any omega in capital Omega, we do know that x of omega is greater than or equal to y of omega, simply because the y random variables we are looking at in the soup definition for the expected value of x are always less than or equal to x. And we've already talked about how you can put a 1 minus epsilon in front because that's only going to make y of omega smaller. So for all omegas in capital Omega, x of omega is greater than or equal to y of omega, and that is greater than or equal to 1 minus epsilon times y of omega. So we do have this inequality here, which, again, we've already talked about 2 slides ago. On this left side here, this x of omega is the limit as n goes to infinity of xn of omega. So if this limit is greater than or equal to this thing over here, that means that the xn omegas will eventually be greater than or equal to this thing for n large enough. That's exactly what we wanted to show. If we take an omega in capital Omega, we can always get this inequality to hold for all n greater than or equal to some capital N. And if that little omega is also in the set capital B sub I, then for all n greater than or equal to some capital N, our omega in B sub I, which is also in omega, is in this set and in B sub I. And when you take this set and intersect it with B sub I, you get B sub n comma I comma epsilon. So what we've just seen is that for any little omega in B sub I, that little omega is in B sub n comma I comma epsilon for all n greater than or equal to some n. So it's certainly in the union, and therefore we have shown that the set capital B sub I is contained in this union as desired, and we're done with our proof. Okay, so some takeaways from today. Let's just wrap it up. We know that if x is a simple random variable with a representation looking like this, then the expectation looks the same, but we replace the indicator with the probability of the event being indicated. We now have a definition that says if x is non-negative, but not necessarily simple, we can define the expected value of x as a supremum. We showed that for every non-negative random variable x, there exists a sequence, xn, of non-negative simple random variables that are increasing to x. And we have shown that in this case, we can take the expectation through the limit. So how might you use this? I honestly wouldn't use it. I would wait until we built up more machinery to make things easier. It's kind of like regular calculus where you learn to integrate by drawing boxes and taking a limit, but then you learn some rules of integration. But if you wanted to try this out, here's an example you might want to try. This video is getting a little long. I am going to end it here, but if you stick around until after the little outro, there will be a couple of minutes where I basically do this example. I won't really talk through it too much. It'll more be something where you can pause the video and check your work. If you want to run through this example, the answer is 2. Otherwise, I will see you in the next one. Okay, if you're still here, I assume you want to see that expectation worked out in all its glory. There are definitely easier ways to do this coming up, but I'm going to do this very fast, and in a lot of cases just give you the answer, and you could pause the video and work it out and see that you can match the answer at each stage. So our random variable x of omega looks like this. It's defined to be -2 times the natural log of omega. And this is our construction in this video, not the only one to be used, but our construction for simple random variables. So let's get a look at what this looks like when n is 1. Going through this definition when n is 1, you'll get 3 pieces. You'll get x1 of omega defined to be 0, 1/2, or 1 on these different regions. So pause the video and check if you need to, and make sure you're with me before going on. In this case, we know that our x of omega is -2 times the log of omega. If I were to plug that in here, here, and here and solve for omega, I can write this out in terms of like a function of omega. I'll get 0, 1/2, and 1, where omega is in these different regions. And if I do a quick and ugly sketch of this, then we get a step function looking like this. And the green parts are my x1 of omega, and this should all look like it's underneath. The scale is way off because I didn't want to deal with how small an e to the -1/2 is, but generally this is the idea. Now, what is the expected value of this x1 of omega? I'm going to take each value, the 0, the 1/2, and 1, and multiply by the probability measure of these intervals. We are using Lebesgue measure in this example, so I'm just going to take right minus left. So it looks like this, and we get this. Done with the expected value of x1. Let's do one more before generalizing it. Let's try to write out x2 of omega, taking our formula. Go do it in slow motion if you want, but you should end up with 0, 1/4, 2/4, 3/4, etc., up to a top of 2 on these intervals. And you'll notice here I've already translated x of omega being between two numbers to what it means for omega. So another step function, I'm not going to try to draw this one, but let's compute the expected value. I'm going to take each of these step heights and multiply by the probability measure of those defined intervals, but we're using Lebesgue measure, so it's just the length of those intervals, right minus left, and you get this. This doesn't look like it's going to be easy to compute, but check this out. I have a 1/4 times e to the negative 1/8, and then I have a negative 1/4 e to the negative 2/8, but over here I have a positive 2/4 e to the negative 2/8, and those I can subtract and get a 1/4 e to the negative 2/8. And you'll keep getting that kind of, I'm not really telescoping, but cancellation of things, and we'll end up with just a 1/4 in front of each of these types of e terms all added together. So 1/4 e to the negative 1/8 plus 1/4 e to the negative 2/8 out through 1/4 e to the negative 1. Pause the video and check it out. We can add this up. This is a finite geometric sum. If you define r to be e to the negative 1/8, then we've got 1/4, and we've got an r plus r squared up to r to the 8th. And leave it in the comment section if you want me to talk about finite geometric sums, but this is going to add up to this, where again, r is e to the negative 1/8. And you could plug that back in and see what it is. It's not going to be very nice. I will actually plug it back in when we do this for the generic nth step function, the simple random variable x sub n, because we are going to need to get it in closed form and take a limit, but we're basically done with the expected value of x2. So now let's do it in general. We're going to get all of these pieces and all of these funky looking intervals. Pause it and check it if you're playing along here. Let's compute the expectation. I just get each of these coefficients times the measure of these intervals. We are using Lebesgue measure, so we can do right minus left. And we get something that looks like this. I've got a 1/2 to the n times this e term. Over here, I have a negative 1/2 to the n times this e term. But over here, I have a positive 2/2 to the n times this e term. And when you combine them, you'll just get a single 1/2 to the n times this e term. You'll get the same sort of thing we had before, kind of telescoping, but nothing's disappearing. It's just simplifying really nicely. And we end up with 1/2 to the n in front of all of these e terms added together. Again, it's a finite geometric sum. If you define r to be e to the minus 1/2 to the n plus 1, and when you compute that geometric sum, you get this. I'm going to need to plug the e's in to take the limit. Let's take the limit. This looks horrible, but I think it's actually not so bad if you do it. Note that this term goes to 1 as n gets large. This denominator here goes to infinity. We're getting something like e to the 0. This thing is going to 1. This term over here is also going to 1 as n gets large. As n gets large, we're getting like e to the negative infinity, which is going to 0. So 1 minus that is going to 1. But the rest of this, this part's going to 0, and this part's going to 0. That was a technical mathematical. And so we need to deal with this L'Hopital's rule. I know that's what you were thinking. Let's do it to find the limit of the remaining part, because the other parts are going to 1. Okay, I want the limit of 1/2 to the n over 1 minus e to the minus 1/2 to the n plus 1. As n goes to infinity, according to L'Hopital's rule, this is going to be the same as the limit if we take the derivative with respect to n of the top and bottom. I don't even want to do this, so I'm going to leave. I don't want to take those derivatives. They're not that bad, but I'm going to leave the limit, the derivative on top, because when we take the derivative on the bottom, we'll get 0 minus e times the derivative of the exponent, which looks an awful lot like the derivative up here. If we pull out the negative and pull out a single 1/2, we do in fact see ddn of 1/2 to the n in the denominator as well, and we get cancellation. So we end up with a limit looking like this. As n gets large, e raised to the 1/2 to the n plus 1 is going to 1, because that exponent is going down to 0. So we're getting like an e to the 0, which is 1. We end up with 1/1/2 or 2. So if you go back and follow through what we're doing, This, what we just computed, was the limit of the expectation of xn as n goes to infinity. And that's one way we saw in a theorem today that we can get the expected value of x. So the answer to the example is 2. And now we're really done. So please come back.